Good morning. Hello. Anybody join?
Yes, so there are 7 students.
7 students. Okay. So today we'll discuss about the assignment problem. Assignment problem means, so we have, let us say, there are n number of jobs. So, and we have n number of machine or n number of workers. Each worker is capable of performing all the job, but their processing time or the processing cost are different. Say we are interested to assign a job to a worker or to a machine so as to minimize the total processing cost or processing time. Generally, the cost is proportional to the time. So we say proportional to cost. Say here, so the assignment matrix, what is given here in the problem is n by n matrix. There are n number of jobs and n number of workers. So for each row, one worker on one machine is assigned. So worker 1, worker 2, worker n for each row. Similarly, for each column, jobs are assigned. We can also interchange the jobs and the workers, interchange the sense. The row can be used for the jobs and the column can be for the workers. There is no harm. So we have n number of jobs, just like column 1, column 2, up to column n. In general, the assignment matrix is a square matrix. So, for example, if I am naming C11, the C11 stands for this cost to complete, the first worker, cost to complete the first worker, the first job by first worker. Similarly, C12, the cost, amount of cost to complete the second job by the first worker. Similarly, C11, the cost attached to the last job, nth job for the first worker. Similarly, we have C21, the cost to complete the first job. The second worker can complete the first job. Similarly, the C22, the second worker can complete the second job, etc. Okay. Similarly, C2n, the second worker can complete the, this job n. And this matrix, what we have mentioned, the cost coefficient C11, C12, C1n, C21, C22, C2n, and similarly Cn1, N2 up to Cnn, the cost coefficients, they are generally so positive elements. So, and sometimes, so we change to 0 by subtracting something. We'll discuss about that. So this cost coefficients, so matrix of size n by n is given to you, and here we have n number of workers and n number of jobs, and sometimes you say the worker also this n number of job and n number of machines, machine and job, workers and job. So it depends on the problem. Okay, so our main aim to minimize the total processing cost. If you assign a job to a worker, see, for example, if I am citing an example, something like, say, first worker is assigned to first job, second worker to second job, third worker to third job, last worker to last job. So this is one way, but see, we are going to assign in an optimal manner so as to minimize the total assignment cost, processing cost. But here, if you arbitrarily assign a worker to a job, that may not be optimum. So, for example, if somebody is assigning arbitrarily, this first job you can assign to one of the worker, let us say first worker. So, if first job is assigned, only there are, say, out of n minus 1 jobs, this can be assigned. So this first job can be assigned in, say, n number of way. So first job, so our first worker can be assigned n number of ways. Then once one job is assigned, then n minus number of way you can assign, and you continue. So this problem, if somebody is solving arbitrarily, so n factorial way we can arbitrarily assign, but we have to find an optimal assignment so that the total processing cost is minimum. If n equal to 3, 3 into 2 into 1, so 6 way you can assign arbitrarily. If n equal to 4, 24 ways, and similarly n equal to 5, 120 way. So you see, this may not be, this is not the way to find the optimal assignment. So we have to apply a method. Here, generally in this assignment model, we use a particular algorithm. I'll mention that. So this is the assignment matrix. This assignment matrix is given to us. So we have to solve the problem. Okay. This explanation like this: the element Cij is the cost of assigning the worker I to job J, Cij. So ith worker is assigned to jth job. More meaningfully, it may be thought of this, cost and times, we can say they are proportional. More meaningfully, it may be thought as of the time taken by the worker I to complete the job J, time or cost. So based on the time we count the cost. There is no loss of generality in assuming that the number of worker and the number of jobs are same. See, generally here we assume in our problem number of jobs and number of workers are equal. Number of jobs, and number of workers are equal. If they are not equal, we have to introduce, just like transportation problem, a dummy job or a dummy worker. Depends on the problem. So if there are more workers, we may introduce some dummy job, and if there are less worker, we may introduce some dummy worker. Okay. Say one important assumption we make it that each worker is assigned to one and only one job, and each job is done by one and one worker only. Okay. So in this problem, since we have n number of jobs and n number of workers, we are assigning only one job to one worker, one job to one worker. So we cannot assign more job. So if you are assigning more jobs to one worker, that is a different problem. So in the assignment, so we are assigning, if you are assigning a job to a worker, the variable, we say the ith job to jth, ith worker to jth job. So xij something like, so it will be either 1 or 0. If you are assigning, it is 1, and if you are not assigning, it is 0. So these variables. So here we have the unknown variable, something like xij. This xij are binary, either 0 or 1. In the transportation problem, these our xij were integers, integer variables. So we are finding the value of the Xij, but here all are binary. So in this problem, say out of, as you observe, there are n square binary variables. Xij, I varies from 1 to n and j varies from 1 to n. Altogether, n square number of variables. Out of n square number of variables, only n of them are 1, rest all are 0. So this problem is representing a integer programming problem where the variables are binary, or you can say binary variables. Okay, 0 1 variables problem. Okay. The assignment model is actually a special case of transportation problem. I have told you, in which sources, the workers, and the destinations are the job. Okay, and the number of sources and the number of destinations are equal. Also, from the last assumption, we get that availability at each source, something like AI equal to 1, and demand at each destination also equal to 1, Bj also equal to 1, AI and Bj, AI equal to 1, I varies from 1 to n, similarly Bj equal to 1, J varies from 1 to n. So our decision variable Xij equal to 1 if worker I is assigned to the job J, and 0 if you are not assigning, or you can say otherwise. We can apply the transportation algorithm also to solve the assignment problem, but this is not a very special one. It will be a lengthy process. So we will not use the transportation algorithm. We will use a special algorithm called Hungarian algorithm to solve such problem. So to assignment problem, we will apply Hungarian algorithm to solve the model. Hungarian means, so here our variables, either they are binary. If you are assigning, there it is Xij equal to 1. Xij means if you are assigning, say, worker I to job J, then the variable is 1, otherwise 0. Okay. So here the algorithm what we are using is known as Hungarian algorithm. We will know detail about the algorithm. Okay. So I'm considering a assignment problem. So this assignment problem, so mathematically a matrix is given. This matrix has 4 rows and 4 columns. The 4 rows something like row 1 for the worker 1, row 2 for the worker 2, row 3 for the worker 3, and row 4 for the worker 4. And similarly, there are 4 columns. That is column 1, column 2, column 3, column 4. So these are the jobs. For first column, we are naming it is for the job 1, second column is job 2, and job 3 and job 4. See, whatever the costs are given, you can see in the first row there is a 0. So generally 0 is not available. This 0 we have made by some method. We will discuss about how to obtain a 0. Similarly, you can see in the second row there is a 0. In third row there is a 0. In fourth row there is a 0. And also you can see in first column there is a 0. In second column there is a 0. And third column there is a 0. And fourth column there is a 0. So this is an ideal case what we are observing in this problem. This case always you may not find, but we have to formulate such problem and you have to apply some steps to achieve this. So I am repeating again, in every row there is a 0, in every column there is a 0. So now how do we assign? See, this 0, it is already mentioned there is a 0. If 0 is not there, we have to obtain 0 by some method. We will discuss about that. So Now, what is the solution? The solution say, see, as I have already mentioned, the Cij is the cost. Cij, if you are assigning ith worker to jth job, Cij is the cost to complete that ith, the jth job by ith worker, Cij. But you can see here, if this first worker is completing the second job, the cost is 0. First worker is completing second job. Similarly, third worker is completing the fourth job.
कौन सा वाटर कूलर चलता है मालूम है?
Yes, please. You are saying something? Hello? Is there any problem? If there is no problem, I am continuing. Okay. So we are assigning the first worker to second job. Similarly, we are assigning second worker to the fourth job. Then we are assigning third worker to first job. Then finally, the fourth worker to third job. Now, if this is the assignment, this is the optimal assignment, then what is the cost? Cost is, you see, the cost is sum up all the Cij, wherein you have assigned 0. So 0, 0, so 4, 0, the sum equal to 0. This is the solution. But now how we have got this 0, we'll discuss. And how to achieve, how to assign the workers to the job, that also we'll discuss. But here, this is optimal assignment. So the second 0, first row, the second 0, so there is the 4, 0, that 0 is responding to x, 1, 2. Then the second row, there is a 0, that is representing x, 2, 4. Then in the third row, that 0 is representing say x, 3, 1. In the last row, that 0 is representing x, 4, 3. So these are the variables, all are 1, rest all are 0. But with respect to the variable, the costs are 0, all are 0. 0, there are 4 zeros, so these are the cost. So the solution is like this. What you can mention here, worker 1 to job 2, worker 2 to job 4, worker 3 to job 1, and worker 4 to job 3. In this manner, we can assign. See, this is a simple problem. Already, it looks like as if solution is given, and we are only assigning. So the assignment cost equal to 0. And with respect to W1, means worker 1 to job 2, our variable is here x, 1, 2 equal to 1. W2 to J4, that is x, 2, 4 equal to 1. W3 to J1, that is x, 3, 1 equal to 1. Then W4 to J3, the x, 4, 3 equal to 1. Okay. Note that in any assignment problem, if a cost, so if a constant, say we are saying a small c, a constant is subtracted from the cost of any row or any column, the optimum solution does not change, but the assignment cost decreases or reduces by amount c. This is because in each row we have to assign 1 to 1 and only 1 cell. I'm repeating again. If you subtract a constant in a particular row or a particular column, the solution does not change. But the assignment cost decreases by amount C. This is because in each row we have to assign one to only one and only one cell. This, I'm again going back. This is the assignment matrix. See, in the first row, the elements are C11, C12, C1n in first row. In second row, the elements are C21, C22, C2n. In last row, the elements are Cn1, Cn2, Cnn. I'm considering, let us say, the first row. I'm subtracting a constant. If I'm subtracting a constant, see, from each of the element of the first row, the elements will become something like C11 minus C, C12 minus C, C13 minus C, and C11, C1n minus C. If you are subtracting a constant from the first row elements, this is the outcome. Similarly, if you are subtracting a constant from the first column elements, so the outcome will be C11 minus C, C21 minus C, C31 minus C, then Cn1 minus C. If you subtract a constant, the solution of the assignment problem will not change. However, the cost will change. That will be reduced by C amount, okay, because you are subtracting the constant C, so this will be reduced by amount C, okay. This we will give a sketch, we will prove it. Okay, now I'm coming. Next case here. We note that in any assignment problem, if a constant C is subtracted from the cost of any row or column, the optimum solution does not change. But the assignment cost decreases by amount C. This is because in each row we have to assign one to one and only one cell. Okay. The Hungarian algorithm exploits this fact and tries to find a zero in each row or a column by subtracting the minimum value in that row to get at least one zero. This will explain in this manner. The second problem is like this. This is also a 4x4 assignment problem. There are 4 workers and 4 jobs. We are going to assign one worker to one job only. So what is the optimal assignment? We have to know from the problem. Are you able to hear? Hello?
Yes, sir.
Any problem? Or any query? Have you received? I have sent the transportation problem, the notes. Have you received? They are big files. Some files are also not going. Have you received my file?
Yes, sir. We received the mail, sir.
Okay. So what I am mentioning here, this is what the matrix is given. It is called assignment matrix. It is not transportation matrix. It is assignment matrix. Generally, the matrix is a square one. It has n number of rows and n number of columns. Presently, this matrix has 4 rows and 4 columns. Some constants are given here. You can see 8, 6, 5, 7, 6, 5, 3, 4, 7, 8, 4, 6, 6, 7, 5, 6. What are the constants? These are simply the cost involved by worker, let us say, if I'm talking about the first row, the cost attached to the jobs, if the first worker is completing the first job, he takes 8 units. The cost is 8 units. Second job, 6 units. Third job, 5 units. And seventh job, that is the fourth job, 7 units. But now, what is the ideal one? So ideal means, so if you think, so we must assign only, let us say, the one job is available, sorry, one worker is available. So we will assign the first worker to the job 3 because he takes minimum time to complete the third job. Because among 8, 6, 5, 7, 5 is minimum. So he's taking least time, that is to complete the third job, that is the 5 units. Similarly, if you talk about the second worker, he takes 6, 5, 3, 4. He also takes minimum time, that is the 3 units to complete the third job. Okay, third job. Now we are coming to the third worker. He takes 7, 8, 4, 6. He also takes minimum time, that is the 4 units to complete the third job. Okay, so and similarly, as you observe, so the fourth worker is also taking the minimum times to complete the third job, that is the 5 units. Now, see, we have some priority, not only the first, only one job, there are several jobs. So we cannot assign one job to several workers. We have to assign one job to. So naturally, what will happen here? 5, 3, 4, 5. So we will assign whoever has taken the minimum time. So we observe, so among all, so second worker is taking minimum time to complete the third job. So he may be assigned to complete the third job. Second worker may be third job. But this is not the way. So we have to learn, say, how to achieve a solution using the Hungarian algorithm. So first thing what we should do, so take the row wise minimum. Row wise minimum, first row minimum is 5, second row minimum is 3, third row minimum is 4, and fourth row minimum is 5. So what we should do? We should subtract the 5 from all the first row elements. So as a result, the 8 will be 3, 6 will be 1, 5 will be 0, 7 will be 2. Similarly, we'll subtract 3 from all the second row elements. So if you subtract, the 6 will be 3, 5 will be 2, 3 will be 0, and 4 will be 1. And similarly, we subtract 4 from all the third row elements. If you subtract, 7 will be 3, 8 will be 4, 4 will be 0, 6 will be 2. And similarly, we will subtract 5 from all the fourth row elements. 6 will be 1, 7 will be 2, 5 will be 0, and 6 will be 1. So what will happen? So we are finding a 0 in every row. First row there is a 0, and second row there is a 0, third row there is a 0, fourth row there is 0. So after achieving this, we'll move. So we are finding this is the outcome. First row there is a 0, second row there is another 0, third row there is 0, and fourth row there is 0. What will happen further? Now we'll see What is the minimum in the first column? Minimum is 1. In second column, minimum is again 1. In third column, already there is 0. There is no question of looking for minimum. Minimum is 0 already. And in the fourth column, there is minimum is 1. So further, what we should do? We subtract from the first column 1. From the second column, we subtract 1. And from the fourth column, we subtract 1. Okay. Why do we subtract? If you subtract, we'll find in every row, in every column, there is 0, and in every row, there is 0. That is the requirement. So after subtracting, we must find every row there is 1 0, and every column there is 1 0. As a result, we have this is the outcome. So in first row, of course, you can see there are 2 0. In second row, there are 2 0. In third row, there is 1 0. And in the fourth row, there are 3 0. Okay. So here, the steps we have introduced. What is the step? From each entry of a row, we subtract the minimum value in that row and get the following cost matrix. Okay. After subtracting the minimum value, this is the cost matrix. Then step 2, from each entry of a column, we subtract the minimum value in that column and get the following reduced cost matrix. So this is the cost matrix we have obtained. Further, step 3, now we test whether an assignment can be made as follows. If such an assignment is possible, then it is an optimal assignment, otherwise not. Okay. Say, how do we assign? Examine the first row. If there is only 1 0 in that row, then assign a 0 with a square, and other zeros in that column, say, if you are finding there is a 0 in a particular row, we assign that 0, and other 0 in that column. So we must cross out. Next, examine the other rows and repeat the above procedure for each row and having 1 0. If a row has more than 1 0, do nothing to that row and pass on to the next row. Here, after subtracting the minimum value from row and column, this is the reduced matrix. In this reduced matrix, so we are examining this first row has 2 0, second row has 2 0, third row has 1 0, and fourth row has 3 0. So what we should do? So we are selecting row number 3, which has only 1 0. Then that 0 we are assigning. So that 0 we are assigning with a square. Okay. And once you are assigning that 0, all the 0 in the same column we must cross. Okay. So same thing we are doing here. We are assigning to this, and all the 0 we cross. Okay. After that, what we are finding? After that, we are finding. So first row already 1 0 has gone, only 1 0. So we must assign to this 0. We are assigning. Then we cross other 0 in the same column. So here we are assigning to this. Okay. And there is no 0 in the same column. Then after this, you can see here. After this, you can see here. in the second row, there is a 0. So we are assigning to this 0, and we are crossing on another 0, which is there in the last row. We cross that one. So we cross that one. First time we're assigning this, second time we're assigning this, third time we're assigning this. And finally, you can see here, in the last row, there is 1 0. We are assigning to that 0. And as a result, this is our complete assignment. So what is the solution here? So first worker is assigned to the second job. Second worker is assigned to the fourth job. Third worker is assigned to the third job. And fourth worker is assigned to the first job. Now, if you are assigning in this manner, what is the solution? The solution is like this. X12 equal to 1, X12 equal to 1, X24 equal to 1, X33 equal to 1, then X41 equal to 1. Okay, so in this manner, you can see here. So with respect to the solution here, X12 equal to 1. So, and we have reduced something. So as a result, this value should be counted, that is 6 unit, 6. Then X24 you can see here, X24, this with respect to this, 6 plus 4, 6 plus 4, that is 10 unit. Then X33, that is 4, 6 plus 4 plus 4, that is 14 units. Then X41, that is 6. Altogether, we have 20 units. So same thing we are naming here. So worker 1 is assigned to job 2. Worker 2 is assigned to job 4. Worker 3 is assigned to job 3. Worker 4 is assigned to job 1. And the optimal cost, we are adding the optimal cost. So altogether it is 20. So directly I'm seeing the matrix and there I'm adding, or you can add all these things, say P1, P2, P3, P4, Q1, Q2, Q3, Q4. So whatever you have subtracted, that is equal to 20. So you can see here how it is becoming 20. So we have subtracted 5, 3, 4, 5. So 8 plus 4, 12 plus 5, 17, and 1, 1, 1, 17 plus 3, that is 20 units. So altogether, our minimum cost to perform all the jobs by the 4 workers equal to optimal cost equal to 20 units. If the final stage is reached, that is all the 0 are either surrounded or crossed, and if there is no surrounded 0 in each row and column, it is not possible to get an optimal solution at this stage. We have to do some more work. Again, we illustrate with a numerical example. The next problem says, if in the final stage, so final stage is reached, that is all the 0 are either surrounded or crossed, and there is no surrounded 0 in each row and each column, it is not possible to get an optimal solution at this stage. We have to do some more work. We'll consider another numerical example and discuss about this problem. Okay. Is there any doubt in this case? Whatever we have discussed? Hello? Is there any doubt? Are you there or not?
Yes, sir, we are here.
No, what I discussed. Do you find any doubt how we are assigning? I will repeat again. So I have taken the first example. In first example, there are 0, and ultimately that 0 we are assigning. In second example, there was no 0. We have established some 0 by subtracting the minimum value in each row. You are taking the minimum value in every row, and you are subtracting. Similarly, taking the minimum value in each column and subtracting, and you are finding a 0 in every row and every column. Then you are assigning. Okay. So when we are assigning, we have observed in first row there is an assignment. In second row there is an assignment. In third row there is an assignment, and fourth row there is assignment. Apart from that, we have seen in every column there is an assignment. In first column there is an assignment. In second column there is an assignment. In third column there is an assignment. In fourth column there is an assignment. So in every row and every column has an assignment. If this is achieved, then we have got an optimal solution. If this is not achieved, we have to do some more work that we are going to discuss. See, let us discuss. This is a unbalanced assignment problem. Unbalanced assignment problem means, so here there are 3 workers and 4 jobs. Since in unbalanced, we have to add one more worker. The 4th worker we have to add to do this problem. As a result, so once you are adding the 4th worker, so processing time of performing all the jobs, all are 0 in this manner. 7, 5, 8, 4, 5, 6, 7, 4, 8, 7, 9, 8, and 0, 0, 0. So why it is so? Because once you have put a fictitious worker, that is the 4th worker, so this is ideal in the sense, so the processing cost all are 0 for all the jobs. Job 1, job 2, job 3, processing cost is 0. Okay, so we are avoiding this. So as a result, what is happening to this? So this is becoming the assignment matrix is becoming a 4x4 assignment matrix. If it is becoming 4x4, then we will be able to process. Otherwise, we cannot. So since it is not 4x4, we have added a fictitious worker, and now it is becoming 4x4. Okay. So with respect to this, so we have to find the minimum in every row. In the first row, minimum value is 4. Second row, minimum value is 4. Third row, minimum value is 7. And fourth row, minimum value is 0. Already all are 0. So we subtract. So after subtracting, we find 3, 1, 4, 0, 1, 2, 3, 0, 1, 0, 2, 1, and fourth row, all are 0. So what is happening? So we will check again. What is the minimum value in the first column? 0. Second column 0. Third column 0. And fourth column also 0. Okay. Now, so in this problem, step 2 is not needed. We now apply step 3 and get the following table. Okay. Say how do you can see here? We are going to assign. The first row has only 1 0. So we assign to this 0, and you cross other 0 in the same column. So we are assigning to this, and there are two other 0 we crossed out. So once we have, then, so this, the last column there is 0, that is already gone. Now we are coming to third row. Third row, there is a 0. Third row, there is 0. And we assign to this 0, only one 0 we assign, and you cross out other 0 in the same column. So this you cross out. Then ultimately in the last row, there is only 1 0. Okay. 1 0. Say we assign to that, and this is your outcome. Now, what do we find here? First row, there is a assignment. Second row, there is no assignment. Third row, there is an assignment. Fourth row, there is an assignment. And similarly, you can see here on the first column, there is an assignment. Second column, there is an assignment. Third column, there is no assignment. And fourth column, there is an assignment. But since third column has no assignment and second row has no assignment, so this is not a complete solution. We go to step 4. What is the step 4? The step 4 is like this. We now draw minimum number of vertical and horizontal lines to cover all the 0. So manually we draw minimum number of vertical and horizontal lines to cover all the 0. So what we have observed, so using one horizontal line, the last row, and two vertical lines, we can cover all the 0. We can cover all the 0. So whatever you have covered, that is the covered element, and we find rest of the elements are uncovered elements. 3, 1, 1 in the first column. In the third column, 4, 3, 2. These are the uncovered elements. Among all the uncovered elements, we find the minimum. Among all the uncovered elements, we find the minimum. The minimum is 1. This 1 is subtracted from the first column, and this 1 is subtracted from the third column. And also, whatever you have subtracted, that amount is added where you have added. So at the crossing of the horizontal and vertical lines, what you have drawn at this position, that is the first row, say fourth row and second column, and fourth row, third column, that amount is added. Okay, and you get a new matrix in this manner. So once you are subtracting, so we have here the elements like say 2, 0, 0. Earlier it was 3, 1, 1. You are subtracting say 1. So it is becoming 2, 0, 0. And in the third column, 4, 3, 2, we are subtracting 1. So that is 3, 2, 1, 3, 2, 1. You can see here 3, 2, 1. And this at the crossing of the horizontal and vertical lines, that was 0. We are adding 1. So at this juncture, so 1, and here also 1. So this is the new matrix. And this new matrix, we are going to assign. Say, how do we assign? The first row has a 1, 0. We assign to this and cross out all the 0 in the same column. So this you assign and cross out. Then we have in the second row, there is 1, 0. After that, we assign to that. and cross out all the 0 in the same column. And finally, in the third row, there is a 0, only 1 0. So we assign to that. Okay. And at the last stage, we have there is 0 in the fourth row. We assign that also. So this is our optimal assignment. So we have, say, in the first row there is a 0. In second row there is an assignment. In second row there is an assignment. In third row there is an assignment. In fourth row there is an assignment. In the first column there is an assignment. In the second column there is also assignment. And the third column there is an assignment. And the fourth column there is an assignment. This is an optimal allocation. Say optimal allocation, say W1 mean the worker 1 to job 4, worker 2 to job 1, worker 3 to job 2, and worker 4 to job 3. So in this manner we have assigned. So job 3, the job 3 is not done by any real worker. The job 3 is not done by any real worker, but the optimal cost you can see here, that is the P1, P2, P3, P4 plus U whatever you have added here. So that is altogether the optimal cost is 16 units. Okay, that's all. Now we have another problem. You can see here. This is clear or any problem? Hello? Hello? Are you able to hear?
Yes, sir.
Yes, sir, we can hear you.
Okay. So we are moving to the next problem. So this is assignment matrix. So this assignment matrix, as you observe, the size is 5 by 5. There are 5 workers and 5 jobs. Okay, 5 by 5, and the cost coefficients are given. And as per our steps, so we find the minimum of every row. First row minimum is 2, second row minimum is 2, third row minimum is 2, fourth row minimum is 2, and the fifth row minimum is 6. We subtract. So we subtract the minimum value from each row. After subtracting, we find the reduced matrix. The reduced matrix in this manner. Okay. Reduced matrix. And similarly, so we check whether every row there is a 0, every column whether there is 0, every first column there is no 0. So minimum is 1. So we subtract the second column, the minimum is 2, we subtract. So third column is already achieved. And the fourth column, minimum is 1, we subtract 1 from all the elements. And fifth column, minimum is 1, we subtract. So after subtracting, this is the reduced matrix. This reduced matrix, we try to assign in this manner. So we check what is happening. In the first row, there are 3 0. It is not possible. Second row, there is only 1 0. This is possible. We assign to this and we cross out all the 0 in the same column. Okay. We assign to this and we cross all the 0 in the same column. Okay. Then we come to the third row. Third row, there is only 1 0 after that. So we assign to the third row and we cross all the 0 in the same column. So then we have here in the fourth row, there is only 1 0. We assign to that. So, and we complete. But we check whether every row and every column has a 0 or not, has an assignment or not. First row, there is an assignment. second row there is assignment, third row there is assignment, fourth row there is assignment, but fifth row there is no assignment. Similarly, first column there is 1, second column there is 1, third column there is 1, fourth column there is 1, fifth column there is none. Fifth row and fifth column there is no assignment. So what do we do? So we draw minimum number of horizontal and vertical lines to cover all the 0. So these are the minimum number of horizontal and vertical lines. 3 vertical lines, 1 horizontal line. So after that, whatever the elements remain, these elements are known as uncovered elements. Among all the uncovered elements, 5, 3, 5, 2, 4, 2, 2, 3, minimum is 2. We subtract 2 from all the uncovered elements and we add that 2 at the crossing of the horizontal and vertical lines. So there are 3 crossing you can see here, 4, 0, 7. So it should be included something like increased by 4 will be 6, 0 will be 2, 7 will be 9. Okay. 6, 2, 9. Okay. And all 0. So this is the present form of the assignment matrix. So for this problem, we like to assign. So you can see here, with respect to this problem, so first row has 2, 0, second row has 1, 0, third row has 3, 0, fourth row has 4, 0, and fifth row has 2, 0. So we'll start with the second row. We assign to this element 0 and cross out all the elements. So we assign to this 0 and cross out all the elements. Okay. So first is done. Now, after achieving this, so second row, we have 3, 0, already 1 has gone, then another 2, so it's not possible. So then we have third row is also not possible. So actually it is possible for the hello. Here, so as I discussed earlier, so in the fifth row there is 1, 0 has gone already, 1, 0, so we assign to that. So after assigning, so we have assigned second row and fifth row. So now we'll talk about the column. So column, you can see there is a column. So we see in the fourth column there is 1, 0. So we assign to that. So then and we have the fifth column there is only 1, 0. Sorry, we talk about the first row. So the first row there is 1, 0. So we assign to that, and in this manner we complete the assignment. So this assignment is something like this. Say W1 to J4, W2 to J3, W3 to J2, W4 to J4, and 555 to J1. Okay. And what is the optimal cost and assignment cost? The optimal assignment cost is 21 unit. Okay. This is all right? Hello?
Yes, sir.
Okay. See, I like to discuss something, say more about, as I mentioned you, whenever we are subtracting a constant from a row or a column from the coefficient matrix, the optimum solution is not changed, but the optimal cost is changing. So we'll discuss about that. So this is a problem, assignment problem. You can see here there are 4 jobs and 4 machines. The machines are nothing but the worker. Here you can say M1, M2, M3, M4. Okay, any manner you can write, no problem. So generally it is minimization type problem. Our decision variables are binary. So see, n equal to 4. If somebody is trying arbitrarily solution, there are 24 feasible solution, 4 into 3 into 2 into 1, because first, you can assign to first machine any 4 job. Once 1 job is assigned, then to machine 2 any 3 job, then machine 3 any 2 job, and machine 4 1 job. So altogether 4, 3, 2, 1. So something like say 24 assignment is possible. 24 solutions are feasible. Among all the feasible solutions, we are looking for the optimal solution, which is minimum. Okay, this question is like this: if you subtract or add a constant, either C or a K, from a row or a column, and assignment matrix, the solution of the problem remain unchanged. The solution of the problem remain unchanged. Solution remain unchanged. However, the cost either it is reduced or increased by that constant. Okay, say how we can prove it? We can prove in this manner. See, in the linear programming problem, if you add a constant to the objective function, the solution is not changing. Only the cost, the minimum value or maximum value is changing. The solution is not changing. So the problem is like this. We want to minimize Z. Z is something like, say, if I'm considering I varies from 1 to 4, J varies from 1 to 4, Cij into Xij. This is our objective function. And in this objective function, we have set of constants. These constants are like this. You can see here, J varies from 1 to 4, Xij equal to 1. In every row, there is a 1. In every column, there is a 1. Summation of I varies from 1 to 4, Xij equal to 1. In every row and every column, there is a 1. Okay, the variables are binary. So this, we are adding or subtracting a constant. So if you subtract the constant, you can write in this manner. So Z minus K you are subtracting, that is summation over I varies from 1 to 4, J varies from 1 to 4, Cij, Xij minus K. This K I am subtracting. So how I am subtracting? I am subtracting in this manner. You can see C11 minus K into X11, C12 minus K into X12, C13 minus K into X13, C14 minus K into X14. Okay, this plus, see, first row I have not taken in this summation. I varies from 2 to 4. First row I am not taking, so I starts from 2 to 4. J varies from 1 to 4. Cij, Xij, 1 is less, and I can simplify in this manner. So if you simplify, this will be together. You can see. So k times x11 plus x12 plus x13 plus x14. This x11 plus x12 plus x13 plus x14 equal to 1. So this will be actually k. This will be actually k. So this one. So once you subtract, this new objective function is becoming z dash. Okay. So z and z dash, they are only k amount either increased or reduced, but the solution is not changing. Solution remains same. So solution of the original problem is same as the, if you subtract a constant from every row and every column, so this remains same, but these cost coefficients, the cost is reduced by the k unit. Okay, that is the answer. Okay, so this you can write in this manner: C11 dash x11, C12 dash x12, C13 dash x13, C14 dash into x14 plus this. So subject to the constraints. So what is the conclusion? If you add or subtract a constant, okay, the objective function value will be changed. However, the solution will not change. A small example. Here I am just stating the example 1. Are you able to see this slide? Hello?
Yes, sir.
Okay.
Yes, sir. We can.
Now what I told, if you subtract a constant from a row or a column of a assignment matrix, the solution is changing, not changing. The cost is only changing. Solution remains as it is. The reason is because when you subtract, this is suppressed. This, the assignment problem, these constants are like this. This you want to minimize, and our constant something like j varies from 1 to 4, xij equal, that is equal to 1. I varies from 1, 2, 3, 4. Similarly, summation of our I varies from 1 to 4, xij equal to 1, j equal to 1, 2, 3, 4, and all the variables are binary. So we are considering only one row, let us say first row or first column. So if you are considering first row, so what is happening? So this is our objective function. So minus k, I can write k into 1. And what is 1? That is x11 plus x12 plus x13 plus x14. This is equal to 1. So here, this I'm separately considering the first row and subtracting, and all the other rows I'm keeping intact. That is, we are writing summation of our j varies from 2 to 4, j varies from 1 to, I varies from 2 to 4, j varies from 1 to 4, Cij, Xij. This here, excluding the first row, other rows and columns are considered. The first rows are presented in this manner. Okay, the first row. So as a result, we are finding this is a new problem. So the first problem and second problem, the optimum solution is same. However, this costs is different. That we are saying. Okay. So this is a problem, a 3x3 assignment problem. The cost coefficients are given in this manner: 2, 9, 4, 7, 5, 3, 6, 1, 8. These are the cost coefficients. And what is the main ambition? Main ambition to assign the machine to the job. So you can assign one job to one machine. So, it may happen there may be multiple optimal solution. So if multiple optimal solution, also you can find out. So in this problem, so we find the row-wise minimum. Row-wise minimum is 2 here. First row, second row 3, third row 1. We subtract. After subtracting, so after subtracting, what is happening here? So the 2, 3, 1. So that is 6 unit you are subtracting. So we have here, if you subtract, so this will be 0, 7, 2, second row 3, 4, 2, 0, third row 5, 0, 7. Okay. Now the question is how we assign. How we assign. So we select a row which has only 1 0. But in this problem we find, so every row there is only 1 0. First row there is 1 0. Second row there is 1 0. Third row there is 1 0. So we assign to the first 0, that is machine 1 to the job 1. Once you assign, so that is complete. Then we move to second row. Second row we assign machine to the third job. Then finally we assign machine 3 to second job. Okay. So you can see these are the solution. For example, M1 to J1, M2 to J3, M3 to J2. So here we find every row has a 0, every column has a 0. So using the Hungarian algorithm, we find here x11 equal to 1, x23 equal to 1, x32 equal to 1, x11 equal to 1, x23 equal to 1, x32 equal to 1, and minimum value of z equal to 6. So we have, so minimum value of the objective function equal to 6 unit. It has only one optimal solution. So let us consider some more problems. So which has more optimal solution. Okay. This is the problem here. The next problem. This is the example 2. Example 2, we have 4 jobs and 4 machine. Say how to assign. So if we apply the Hungarian algorithm, so we take the minimum of first row, minimum is 2 units. Second row minimum is also 2 units. Third row minimum is 3 units. And fourth row minimum is 3 units. We subtract. After subtracting, we find, say the first row has 2 0. Second row has 2 0. Third row has 2 0. And fourth row has 2 0. So this is a case. So we observe there may be multiple optimal solution. So since you have 2 0, you can assign to any 0, either to, if you are talking about the first row, there are 2 0. So first row, first column there is 0, and we have first row, third column there is 0. So you can select the first 0 and you assign to that. So we are assigning, and you cross out all the 0 in the same column. Okay. Then, so we are talking about the second row. Second row has 2 0. So we assign to the 0 and we cross out all the zeros in the same column. Okay. So then see here, whenever we are selecting 1 0, other 0 must leave. Okay. So because you are assigning either J1, so M1 to J1 or J3. If you are assigning to J1, then J3 cannot be. Okay. So similarly, third row has 2 0. Okay. So you are selecting the third row. Okay. And we are assigning to that. And finally, we are selecting, so to fourth row. So this is a solution. You can see our solution is something like, say, x11 equal to 1, x22 equal to 1, x33 equal to 1, x44 equal to 1. And so this solution has altogether say what is the minimum cost? 2, 2, 3, 3. So minimum cost is 10 units. Now, is there any? See, if instead of the first, if you are selecting the second zero, so we can also find another solution. So this solution also you can also obtain using the same rule. Okay. The next example. Okay. The next example is like this. So there are 4 machines and 4 jobs. So we find the minimum in the first row, second row, third row, fourth row. The minimum equal to first row is 2, second row 3, third row 1, and fourth row 3. After subtracting, so we find the reduced matrix. So in the reduced matrix, we find, okay, there is at least one 0 in the first row, in second row, in first column, second, third row, and fourth row. So we assign. How to assign? So we assign. In this problem, what we observe, every row has 3 zeros. Instead of 1 or 2, it is a 3 0. Every row and column has 3 zeros. So we assign to one of them and we proceed. So once you're assigning, so we cross out the other rows in the same. So we are assigning to this and we cross out the other 2. And similarly, we assign to this and cross out the other 2. And we assign to this and proceed. So here in this problem we're assigning M1 to J2, M2 to J1, M3 to J4, and M4 to J3. So and the minimum cost equal to 9 units. This example 3 has 3 optimal solution, and we have only stated the 2 one. You can find the other 2 in the similar manner. Okay. So this is a problem. The fourth example. Can you see the fourth example? Hello?
Yes, sir.
Okay. Please try yourself the fourth example. For the example, so the first row, the minimum is 1. Second row, minimum is 1. Third row to 0. Fourth row 2, and fifth row 1. We subtract 1 from all the first row elements, 1 from the second row elements, 2 from the fourth row elements, and 1 from the fifth row elements. After that, we are finding this is your outcome. Okay. So the first row has a 0, second row has a 0, third row has a 0, and fourth row has a 0, and fifth row has 2 zeros. Okay. So we assign in this manner. Once you assign, so first row, our assignment is machine 1 to job 4. Then for the second row, machine 2 to job 3. For the third row, machine 3 to job 2. And for the fourth row, machine 4 to job 1. And for the fifth row, that is machine 5 to job 5. Okay. And what we have obtained here? So we are finding the minimum cost. Minimum cost equal to, you can see that is 5 units. Okay. Z equal to 5 units. The example 4. So here in this example, so we have to apply all the steps. This is a 4 job and 4 machine problem. So we observe the minimum, the first row that is 5, minimum in the second row that is 6, minimum in the third row that is 7, minimum in the fourth row is 4. We subtract. After subtracting, we find 0 in every row and every column. Okay, so we find, so these are the 0 and we assign, we try to assign. So after assigning, we find, so in the first row, once you have assigned, other 0 you can cancel here. In second row there is, there are 2 elements we cannot assign, and third row there is no 0, and fourth row there are 2, and we talk about the second column. First column already done. Second column there is 1 we have assigned, and we have so we find here assignment something like 1, 2, there is 3 assignments. So this is not the complete assignment, because in the third row and the third column, which fourth column, there is no assignment. So this is not a complete assignment. So we draw minimum number of horizontal and vertical lines to cover up all the 0. So after achieving that, so we have drawn 1, 2 horizontal line and 1 vertical lines. And so after that, we find there are uncovered elements 3, 2, 2, 1, 4, 3, and the minimum value is 1. So 1 we subtract from all the elements. Then this 1 is added at the juncture. At the juncture means, so here we will add 2 becoming 3 and 3 becoming 4. So 2 becoming in a okay. So finally, so we have like this. So in the first row we have assigned, and second row, once you have assigned first row is done, and second row there are 2 0 we cannot. Third row there are 1 0 we can assign because this is already gone, and in the fourth row there is 1, and first column we have done, second column this is assigned. Okay, so third column, this is the second row we have assigned, and the third column there is an assignment, and we have fourth column there is an assignment. As a result, we have assignment in all the row and all the column. So the minimum assignment equal to 23 units. Okay, this. Here we observe a difference in the transportation problem and assignment problem. What is the basic difference between a transportation problem and assignment problem? Who can say? Hello? What is the basic difference between a transportation problem and an assignment problem?
The assignment problem is binary.
Assignment problem is binary, and transportation problem is
Integer.
Integer. Okay. So what we have discussed here, generally, some few points I like to include. Okay. This is the assignment problem is minimization type. Okay, minimization type. If somebody is posing the problem as maximization type problem, what will happen to the solution? If I am posing the problem instead of minimization type to maximization type, what will happen to the problem? Is it possible to apply the same rule to find the solution or a different rule?
We need a different rule because over here we're looking for the minimum element, there we look for the maximum.
Okay, see, if to you a problem is given maximize z and these are the constants, how to solve? So simply multiply minus sign. Okay, so maximum of z is same as minimization of minus z. Okay, so then we proceed. How to proceed? All the cost coefficients will be negative. So here it will be C11, C12, C13, C14, C21, C22, etc. All will be negative. Okay. Now, what exactly you are doing? So since it is negative, so we like to make some of the elements 0. What will do? So there you are subtracting, and here what will do? You will add some constants. To first row elements, you add some constants. For example, it is given something like minus 10, minus 12, minus 13, minus 14, something like minus 10, 12, 13, 14. So how much you have to add to make it 0? How much you have to add to make it 0? The negative. So we are going to make, see, these are, you see, it is given minus 10, minus 12, minus 13, minus 14. Okay. So as I have already told, so you can add a constant or subtract a constant. If you add or subtract a constant, the optimum solution will not change. Say minus 10, minus 12, minus 13, minus 14. How much you have to add? How much you have to add so that all will be positive or 0?
14.
14, not minus 10, not 10. Because once you are adding, so you will find a 0. Okay, in every, so similarly in second row, second column, and in the third row, fourth row, and similarly first column, second column, and you find the solution. Okay, after finding the solution, whatever you have added, so we have added something, no? So we got the solution for what? We have got solution for the, it was given, the problem is maximization type. We have changed to minimization type. We have got solution for the minimization type problem. Okay. So then multiply minus sign and make it. Okay. So the value of the objective function. Okay. And the optimal assignment to come automatically. Okay. There is no other rule. Okay. Maximum, minimum. So in the transportation problem, similarly, if the problem is given in maximization type, what will do? Problem is given maximization type. There are some changes you will observe because you change into maximization type. Maximization type, for the maximization type problem, say what is happening? For the maximization type problem, the constants are equally type. In the dual problem, the minimization type, if the maximization type problem, the constants are equally type, but the dual problem has minimization type objective function and the constants will be less than equal type or greater than equal type. Hello? Constants will be greater than equal type, not less than equal type. For the transportation problem, originally the problem is minimization type. Generally it is minimization type. So, and the dual one will be maximization type. And for minimization type, the constants are equally type. For the dual will be maximization type, and the constant will be less than equal type, and the variables, dual variables are free. Similarly, if the problem is maximization type, transportation problem is maximization type, the dual will be minimization type. Here, the constants are equally type, and the dual problem is minimization type, and the constants are equally type. It's a greater than equal type. Okay, and the dual variables are free. Same rule we can apply, but generally, please remember the transportation problem always by default the objective function is minimization type. Similarly, for the assignment problem by default this objective function is minimization type, and for the assignment problem, and the variables are binary. For the transportation problem, the variables are integer, but for the assignment problem, the variables are binary. And the problem is a square matrix. The assignment matrix is a square matrix. Number of jobs and number of machines are same. If there is some discrepancy in the number of jobs and number of machines, if number of machines are more, you can add some fictitious job to make it equally type. So if number of machines are jobs are more, sorry, if machines are more, you can add job. If jobs are more, you can add machine and make it always square and solve. Okay. And if you are adding an extra machine, means one row you are adding, all the cost coefficient has to be 0. Similarly, if you are adding one extra job, all the cost coefficient in that columns all are 0. So using that, you have to proceed for the solution. But here, please remember, if you add or subtract a constant from the assignment matrix, the optimal solution is not changing. The optimal cost is only changing. Okay, that you are reflecting in terms of the cost coefficient, in some constant whatever you have added or subtracted. So that you are using, and all the solution among, if there are n square number of binary variables, if only n are non-zero, that is 1, rest all are 0. So only you can mention about the non-zero variables. All the 0 variables are not mentioning. So for example, if I am assigning, in this case, you can see here, out of the 9 such variables, 3 are non-zero. X11, that is 1, non-zero. X23, that is 1, non-zero. X32, this is 1, non-zero. Rest all are 0. So wherever we have marked this 0, 0, 0 with a square, they are non-zero. Rest all are 0. Out of the 9 variables, 3 are non-zero, rest are 0. 6 variables are 0 and 3 are non-zero. If it is 16 variables are involved, out of 16, 4 are non-zero, they are 1, rest of 12 are 0. So in this case, you can see here X11, X22, X33, X44, they are 1, rest 12 are 0. We don't write the 0 variables, only we write non-zero variables. So what 1 stands for? We are assigning machine 1 to job 1, 2 to machine 2 to job 2, 3, 3, machine 3 to job 3, and similarly, finally we have machine 4 to job 4. We are assigning. So once you are assigning, it is 1, not assigning, it is 0. Okay, this. And sometimes, sometimes what do we do? So if for the particular machine, the processing cost is huge for a given job, so that we put big M, and that we should avoid. So certainly that cannot be considered. So if you are, it is something like, say, it is M. M is a large number, so we avoid that. We don't consider. Okay. Generally, it is not huge. It is given with some limit. So with respect to the cost coefficient, we find the reduced cost coefficient and we solve the problem. Okay. Your question paper we have already submitted, so they will conduct the test. I don't know. So when, but they, I think they will notify. Okay. The question paper, the pattern is like this. So there are 10 questions. Hello, are you able to hear?
Yes, sir, you are audible.
Yes, sir, we
Okay.
can hear you.
Okay, there are 10 questions. Each question carries 5 marks. Okay, so 10 into 5, 50. Okay, and questions are from the all the sections. So starting from the simplex, dual simplex, revised simplex, everything is otherwise, because you know everything as per the rule, it should cover everything. Okay, so whatever we have covered till date, everything is included. Okay, so problems is there, theory is also there, right? So simplex method, you know, the integer programming, transportation, assignment, everything is included. Okay, so and possibly they will conduct. Already we have submitted the question paper to the academic section. They will conduct. I don't know when they will conduct, and suddenly the test will be in the offline mode. Okay, date and time possibly they will announce. So, but they have asked us to submit the question by 20th March. We have submitted the question paper. Okay.
Sir,
And
what would be the total time duration, sir? 2 hours or
time
more
is
than 2 hours?
time is 2 hours. Okay, the time is 2 hours. Maximum time is allotted 2 hours. So you see, since there are 10 problems only, so how much time you are getting? And some problem you can quickly answer. Maybe 10 problem around, say, 12 minutes. I think it's possible. 5 minutes is less, about 12 minutes is possible. Okay. I will stop here. Okay.
Hello, sir.
And see, I was asking, you know, whatever you have, the code you have developed, okay, till date, whatever you have developed, so there is no problem. Whatever you have developed, you submit, okay, because you have to grade according to your, you know, some marks are given for that. So we have to assign for that, okay, whatever, because you are solving group wise, you mention, so which year belongs to which group, and please write the names of the students. Okay, and you submit. Don't submit individually, because since I have mentioned you submit the code in groups, you submit whatever you have done, so there is no problem. Okay, but you submit, and that is fine. Okay, we'll stop here.
Yes, sir.
Please tell me.
Sir, this 12th assignment problems, this handwritten PDF we did get, sir.
No. See how many I asked. See, it's not all. Whatever is possible. Okay.
No, sir. This PDF is not sent, sir, in the mail, sir. This handwritten PDF which you are presenting right now.
Not going. Not reached.
Yes, sir. This
Can you
PDF
also
is...
share the transportation problem PDF?
Yes, sir.
So how to send? Should I put in some drive?
Yes, sir. It would be also better.
This is you are getting?
Sir,
No.
10 and 11. This, sir, the previous PDF we got, sir, the blue one, sir, which you are presenting.
No, actually,
previously.
the handwritten, see, the size is becoming big. Possibly that is the reason is not going. Okay. Okay. It is not going, so maybe it, the size, size has some limitation.
Sir, you can upload them on the Teams, MS Teams.
I can upload in the Teams, no? That is possible.
Yes, sir.
Yes, sir.
Okay. Okay, that I'll do it. Okay. So there is no limit for the team?
No, sir.
Okay. The bigger file I can upload there. Okay. Okay, thank you then.